In section 5.3, we are going to talk about the first fundamental theorem of calculus, which is going to help us evaluate, which means give a value to integrals. Now, the theorem is given that f is continuous on the interval a to b, then the integral of f of x dx from a to b is equal to f of b minus f of a, where f is the antiderivative, big F is antiderivative of small x. Okay, now let's get straight into examples. Let's evaluate the definite integral 2x plus 1 dx from 3 to 6. So first off, this is small x. We have to find its antiderivative. Now remember, we learned in section 5.0 that if you have the integral of x to the n, this equals to x to the n plus 1 over n plus 1. This is the power rule of integrals, which we're going to be using over and over and over and over again. Okay, so in this case, we have 2x. Oh, and then also, if you have a constant a, and for proper notation, let me put a dx here. If you have a dx, then that just equals to ax. And then let's not forget the plus c. All right, so we want to evaluate this definite integral. So for 2x, the exponent here is a 1. So we have 1 plus 1 over 1 plus 1, which is going to be x squared over 2. This is just a constant. So according to this, it'll just be 1x or x, and we have that constant c for any antiderivative. And then if you simplify this, 2 divided by 2 is 1, so we're going to get x squared plus x plus c. That is big F of x. Now we want to, so according to this, the integral will equal to f of b minus f of a, where a and b are the limits of integration. So this equals to f of 6 minus f of 3 according to this formula once you find the antiderivative. So f of 6 means we're going to replace the x values with 6. And then f of 3 means we're going to replace the x values with 3. And if we simplify this, we get 36 plus 6 is 42 plus c. We have 9 minus 3, which is 6 plus c. And then if you simplify that, we get 36. Now what happens to the c? Well, you have a positive c and then you have a negative c. So the c minus c are going to just cancel out. And we're left with 36. So in other words, the area under the curve 2x plus 1 between 3 and 6 is going to be 36. We can verify that using geometry if we really wanted to, but we're not going to. And this case, by the way, will always happen where the c's are going to cancel out because we're always going to get f of b minus f of a, so we're always going to get a c minus c. So the c is always going to go away when we evaluate. All right, let's take it. So basically we find the antiderivative, and then it's going to be f of b minus f of a over and over again. The second fundamental theorem of calculus, if there's a first, there has to be a second, is that if we take d dx of a to x of f of t dt, that's going to equal to f of x. All right, so what is this saying? So first off, we're taking the derivative from a constant a to a variable x. Now the derivative matches the upper limit of integration. So the second fundamental theorem of calculus, it takes the derivative of an integral, but it's not just any integral, it's where the derivative, which is d dx, is going to match the upper limit of integration, and the lower limit of integration is a constant, and that'll just equal to f of x. So for example, if we're given f of x equals to 0 to x, t to the third minus 5t squared plus 1 dt, we want to find f prime of x. So what is f prime? Well, f prime is the same thing as the derivative, that's just d dx of 0 to x, t cubed minus 5t squared plus 1 dt. And according to this theorem, because we're taking the derivative with respect to x, and the upper limit of integration is also x, so when you take the derivative of an integral, it'll just equal to f of x, which means we're going to replace every t with an x. So that's x cubed minus 5x squared plus 1. That'll be your f prime of x. And then from there, we're going to find f prime of 3. That'll just be, since this is f prime of x, we're going to replace every x with 3. F double prime of x, so if this is f prime of x, to take f double prime, we take the derivative of that. So the 3 comes down, we get 3x squared minus 10x. 1 is a constant, so that goes away. And that'll be your f double prime of x. So once again, we can use the second fundamental theorem of calculus when we take the derivative of an integral. So they're kind of undoing each other. But the what you're taking the derivative with respect to, so with respect to x and the upper limit, they do have to match. Okay, here's an example. We have f of x equals to the integral from x to 6 of sine t cubed of dt, and we want to evaluate this integral. Now notice that we can't use the second fundamental theorem of calculus because we don't have a ddx. We're not looking for the derivative. We're looking to evaluate the integral. Okay, so let's remember that. Now, first off, we need x as the upper limit. Okay, so because we need x as the upper limit, we're going to switch the 6 and x. Right now we have x to 6, but we want to make x to be the upper limit. So we're going to switch this from 6 to x. And then we learned in 5.2 that if we switch the limits of integration, then we just make this a negative. So this equals to negative 6 to x sine of t cubed. Okay, this is from section 5.2. All right, what's next? So from there, we want to, now we can find f prime of x. So now f prime of x, because now we can match the upper limit of integration with the derivative. So then now we can just replace the x with the t with x, and we get negative sine of x cubed. But we can only do that once we can match the upper limit of integration with the derivative, which is why we had to flip these. And this should have actually, in the beginning, said find f prime of x. So sorry about that. Okay, next we want to evaluate this definite integral. So let's use the power rule of antiderivatives, which again is going to be that if you have the integral of x to the n dx, this equals to x to the n plus 1 over n plus 1. And also if you have the integral of a dx, this just equals to ax. All right, so we add 1 to the, so it's n plus 1 over n plus 1, where n is 2. So we have 2 plus 1, which is 3 over 3. Here, the n value is 1, so 1 plus 1 is 2, so we have x squared over 2. And then for 4, it's a constant, so we get 4x plus c. If I simplify this, 12 divided by 3 is 4, 4 divided by 2 is 2, and then we have a 4x plus c. So this becomes your antiderivative. Now, according to the first fundamental theorem of calculus, if you want the antiderivative between 2 and 7, we're just going to find f of, let me actually write these on the side. We just want to find f of 7 minus f of 2. So f of 7 means we're going to replace all the x values with 7, and then minus f of 2, it means we're going to replace all the x values with 2, which is what I did here. I'm not going to bore you guys with the calculation. You can just put it into any calculator you want to, and you'll get that this comes out to be 1302 plus c. This comes out to be 32 plus c, and then the c minus c is going to be 0, so we just have 1302 minus 32, which will give us a 1270. Once again, we have the integral of x to the n dx equals to x to the n plus 1 over n plus 1, and the integral of a dx is equal to ax. All right, next let's evaluate this definite integral. This one's going to be a little bit more tricky because notice here we're dividing by the square root of x, so we have to simplify that. Now, first off, square root of x, that's equal to x to the 1/2 power, because we have square root is going to be the second root, the 2 is invisible, and to the first power. So if we go from radical form to exponential form, this is going to equal to x to the 1/2. Okay, so we're going to split these up into two separate terms, divide them both by x to the 1/2. We did this way back when we did derivatives. Now, to get this ready for integration, we have to move the x to the 1/2 to the numerator. In other words, when you move it to the numerator, it's going to become negative. Or you can remember the properties of exponents, where if you divide the same base, we subtract the powers. So we're going to subtract 2 minus 1/2. And then here, the x to the 1/2 just moves to the numerator, becomes x to the negative 1/2. When you subtract fractions, we need a common denominator. So on the side here, I wrote down the common denominator. So 2 over 1 minus 1/2. Common denominator is 2, so I multiply the first fraction by 2, get 4 over 2 minus 1/2, which is 3/2. Get really good at fractions, because for integration, and even like when you go to Calc 2, you'll see a lot of fractions, so get very good at those. So we have 2 minus 1/2, which is going to be 3/2. Okay, so now we have the integral from 4 to 8 of 2x to the 3/2 minus 9x to the negative 1/2 dx. Now let's use the power rule of integrals. The power rule of integrals is going to be, you have your n value, which is 3/2, so it'll be n plus 1, which is 3/2 plus 1 over 3/2 plus 1. Here the n value is negative 1/2, so we have negative 1/2 plus 1 over negative 1/2 plus 1. On the side here, I did the calculations for the fractions. So if you have 3/2 plus 1, we need to convert this into a denominator of 2. So we have 3/2 plus 2/2, which is 5/2. Here we have negative 1/2 plus 1, which again is going to be 2 over 2 to get a common denominator, which gives you a 1/2. So both of these can be replaced by 5/2 and 1/2. So we have 2x to the 5/2 over 5/2 minus 9x to the 1/2 over 1/2. More rules of algebra and just dividing by fractions. So we cannot divide by a fraction. So because we can't divide by a fraction, we multiply by the reciprocal of the denominator, which is 2/5. So then the denominator just goes away. And here, same thing here, the denominators go away. And we're left with, on the numerator, we have 2/5 times 2, which is going to be 4/5 x to the 5/2, and then 2 over 1 times 9 is going to be, here we will multiply by 2 over 1, which is the reciprocal. 2 over 1 times 9 is going to be 18x to the 1/2. Okay, so what we have here now is 4/5 x to the 5/2 minus 18x to the 1/2. That is your antiderivative. And according to the first fundamental theorem of calculus, this is going to equal to f of 8 minus f of 4. I strongly recommend you use like Desmos or some kind of a really easy calculator. So for we're going to replace the x first with 8. So each of the x's gets replaced with 8, and then minus, they get replaced with 4, which are our limits of integration. If you simplify all this into in a calculator, we're going to get 104.3038. All right, we want to write this as a integral, write this integral as a sum without the absolute values. So notice that for the first one, the slope is negative. So when the slope is negative, this is going to be 4 minus x. But then we hit this 0.40, and you can see this on Desmos, and then the line starts going up. So when the line starts going up, the slope changes. So we have to add a negative in front of the 4 minus x because we change directions. And if you distribute this negative, this is going to equal to a negative 4 and a positive x. So what we have now is the integral from 0 to 4 of 4 minus x, and then from 4 to 9, because we're only doing between 0 and 9. So this next one is going to be between 4 and 9 of negative 4 minus x, which is basically negative 4 plus x. Okay, which is this thing over here, if you distribute the negative. So then let's apply our laws of integrals. So we get 4x minus x squared over 2 from 0 to 4 plus negative 4x plus x squared over 2 from 4 to 9. Apply the fundamental theorem of calculus for each of these, which I'm not going to do. It's just you're replacing with 4 and then with 0. You're doing it separately. So it's going to be your f of b minus f of a, but you're doing it twice. And this will give you 8 plus 12.5, which is going to be 20.5. And this one we'll do